Okay, welcome back everyone, and we are now starting our discussion about Schwarzschild geodesics or solar system tests. In particular, we're going to talk about orbits and perihelion precession of Mercury and the bending of light around the sun. Really important tests that Einstein did and calculated to vindicate his theory when he was coming up with it. And this material is going to be basically all of Chapter 9, Guidry. So we're going to recap just a little bit. Remember, we had the Schwarzschild solution, and the Schwarzschild solution was a solution to the Einstein field equation, where we had written it in non-canonical form like this. And when we set T mu nu to 0, then we just have that R mu nu, the Ricci tensor, has to be 0. And so to solve this for a stationary mass that's statically constant, we get this solution here. And so we see here what this basically describes is a black hole. And if you see here, we have 1 over 1 minus 2 gm over r. That means that when r equals 2 gm, this term here, which we can call this term here, right, will blow up to infinity. So that's what we call a curvature, not a coordinate. It's a coordinate singularity. So in other words, there's a black hole structure at Rs. What we call Rs is this boundary here at 2 gm. The gravitational attraction becomes so large that nothing can escape, not even light. And so you should get that's why we call it a black hole. So this is saying the black hole has this event horizon at 2 gm. So that's the Schwarzschild metric. But what we're going to do is we're going to actually exploit Gauss's law and make sure we are at some Gaussian sphere that's larger than Rs. So we're going to be at the regime where all of our radial distances are going to be larger than Rs. In that case, we're never touching the black hole. And in fact, then this is actually a good metric to describe the gravitational field of something like our sun, even the Earth, if you're looking at satellite motion. And I know the sun and the Earth rotate, so technically this is not a static solution then anymore. It's still static, but it has a constant rotation that we assume. But the rotation of the Earth and the sun even is not significant enough to deviate much from this solution when we're talking about planetary orbits or perihelion precession of Mercury and those kinds of tests. So this is actually a good gravitational field ansatz for the sun, as long as we're not at this limit. And in fact, nothing is at this limit, not even the sun's atmosphere. So with that said, what we want to do is talk about the geodesics, because the geodesics, right, they tell us about motion of test particles. Now, what could be a test particle? Let's call it test particles. That could be anything like the Earth, other planets, and anything. There's also test particles which we call ZAMOs. Those are zero angular momentum observers. So we're not going to really think about the Earth as rotating in its own right. And again, that the gravitational effects from that are really negligible. So, we know the geodesic equation. I can write the geodesic equation down, which we've already looked at and derived before. And normally, this is what we would need to solve this equation in order to answer questions about. So this is the equation that tells us test particle motion around a spherically symmetric static gravitational black hole like this, or any black hole solution or gravitational field solution. I will say though, we could do this, but this is actually really hard. There's a lot of equations here, 4 equations I guess, and it's kind of difficult. You have to compute all the Christoffel symbols and so forth. There's actually something very nice which gives us or consolidates basically the geodesic equations into one equation, and that's the principle of equivalence. And remember what the principle of equivalence stated is that we have a nice normalization. We have g mu nu of the 4 velocity for an affine parameter tau has to be 1. And I just moved the minus sign over. Now it turns out that for the Schwarzschild black hole, this actually encompasses everything we need to know from the geodesic equations and for our solar system tests. So what we can now do, actually what I want to do is I want to introduce a parameter instead of 1. So I'm going to rewrite this as and I'm just going to call this epsilon. Now epsilon is either going to be 1 or 0. It's going to be 1 for non-zero mass particles. So this is massive particles, but it could also actually be 0, and that's when the particles have no mass, like light. And so in general relativity, we actually have the phenomena that light can orbit a black hole. We know that because light has energy, but and therefore a gravitational force. But more importantly, light is contained inside space-time, so it has to follow the geodesic equation, just like any ZAMO would have to. So let's expand this out using the Schwarzschild metric here. And so for the Schwarzschild metric here, we have G00, right? G RR, G theta theta here, and then G phi phi here. So that means that we expand this out, and we're going to get epsilon. I'm going to write epsilon first. So I have 1 minus 2 gm over r, and then I'll have dt d tau squared. And then we have minus, and I think the book is using lambda, but I'll keep using tau. Shouldn't make a difference. And then here I will have dr d tau squared, and then we have r squared minus r squared d theta d tau squared minus r squared sine squared theta d phi d tau squared. Okay, so the next thing we want to do is make a small simplification, and what we're again what we're going to be looking at is we want to think about the sun, right here, not to scale, but that would be the sun, and then we're going to look at something like the Earth, right, and the Earth is moving around the sun like this in a planetary orbit. So if I'm at the sun and I think about this as the z-axis, right, then from here down to here, that should just be theta equals pi over 2. Okay, so I want to take over here and set theta equals to pi over 2, so we're in the equatorial plane. And that's a fair assumption to make, because we can assume that, well, all planets do orbit except Pluto, but Pluto's not a planet, orbit in the same plane, and we can set that plane to be pi over 2. So what does that mean for epsilon? The first term, nothing changes. Second term, nothing changes. And nothing changes here. Oh, actually, something does change here, because we've picked a value for that theta, so this term is going to be 0, because d of pi over 2 is just 0. And here, sine of pi over 2 is 1. 1 squared is 1. So that simplifies that nicely. Okay. So here's our simplification. What we want to do next is introduce some quantities that can actually help us simplify this, and those are conserved quantities. Okay, so I have my conserved quantities here. Now, if I think about the orbit here, there's 3 things conserved. There's the angular momentum has to be conserved, right? Energy has to be conserved of the particle. There's also something called the Runge-Lenz vector, which is also conserved. But we don't need to worry about the Runge-Lenz vector, because we're not really worried about jet structures and stuff like that right now. So the 2 big things are energy and angular momentum. And if we go back to our Schwarzschild metric, we can see here that the metric does not depend, the metric components never depend on time, and they never depend on phi. So that means there's 2 killing vectors. Without having to solve the killing equation, I know there's 2 killing vectors. Okay, there's a killing vector in t, dt, and there's going to be a killing vector in phi, which is d phi. Okay, so that means I have the components of these 2 killing vectors will be 1, 0, 0, 0, and the phi will be 0, 0, 0, 1. So those are my 2 killing vectors, and what I would like to do is construct the conserved quantities. And the conserved quantities come from Noether's theorem, and they're given to us by the inner product of the killing vector and the 4 velocity, which what that looks like this. So it's the inner product, like I said, of the killing vector and the 4 velocity, I want to write this out with the metric now because this is lowered, right? And the way we define them are raised. So I want to write a g mu nu in here. And sorry, did that wrong. It should be lowered. And so we'll write it like that. So let's see what happens. Let's work it out for the time, the temporal piece. So the conserved quantity, so what I want to do is look at the temporal. So that's going to be g mu nu mu t. Oops, there's a mistake. That should be nu. I'm sure you guys caught that. Now, for the temporal component, keep in mind that the only non-zero part is when mu is 0. Okay. So what that means is that this sum here, this sum here only extends over 0 and the rest are 0. So I'm going to get g0 nu, and then I'm going to have a 1 here from the 0 component there. dx nu d tau. Now, furthermore, if we go back to the Schwarzschild metric here, we see it's only diagonal, right? There's no off-diagonal pieces, which means too that the only non-zero component here is when nu is 0 as well. So I get g0 0 dx 0 d tau. So g0 0 is going to be minus 1 minus 2 g m over r dt d tau. So that's a conserved quantity, and we call this E. Let's call this capital E. Let me check my sign definition. Actually, we call this minus E, and the book calls that minus E, yeah. So this is minus the energy, conservation of energy here. So that's nice. Let's keep this one in mind here. Let's work out the angular momentum conserved quantity. So obviously, you know, time, temporal translations, time translations, invariance gives you energy. Angular translation invariance has to give you angular momentum. So let's look at angular momentum here. So we'll have and now the only non-zero piece is when this is 3 or phi, right? So this will be g3 nu and then a 1 dx nu d tau. But also here, it's diagonal, so the only non-zero piece is when nu equals 3. So we'll get g3 3 dx3 d tau. So g33 in the Schwarzschild metric is r squared sine squared theta, but remember sine squared theta is 1 because we picked theta equals pi over 2. So I get r squared d phi d tau. And so we call this L. For angular momentum. So this gives us our conserved quantities, and let me write E down next to it. And so we'll have 1 minus 2 GM over R, and that's E. Just so we have them together. So what I want to do is take my equation here, put that down here. So what am I going to do here? What I would like to do is let's multiply through by 1 minus 2 GM over R, the whole equation. Let's do that. So I'm going to have 1 minus, and you'll see why this is helpful here in a minute. And so what I'll have here is I'll have this term squared minus, and here I'll just have d r d tau squared. That's nice. This seems like it gets a little complicated, but it doesn't really. But let's just write it down. And then r squared. And what I'm going to do actually is write this as 1 over r squared, r to the 4th, or let's write it like this: r squared, like this. So why did I do that? Well, look here. What we have here now is e squared, and that's a constant. Okay, and what I have here is L squared, and that's a constant too. So that's very nice. So let's keep writing this down with these simplifications. So I have E squared minus and then minus 1 over R squared 1 minus 2 GM over R L squared. Okay, so I'm just gonna box this for now because this here is a very good starting point for a lot of other problems, so I want you to keep that in mind. But what I want to do next is do a couple of redefinitions that are convenient. And what I would like to do first is divide some things by 2. And let me solve for e squared in this case. So I'm going to say e squared. Let's put e squared, solve for e squared here. And in fact, I'm going to divide out e squared by 2. And let me write down the this term here. So I get 1/2. So I'm going to have minus 1 minus 2 GM. No, there's no minus there. Sorry. I was looking at the wrong thing. So I have 1 minus 2 gm over r epsilon over 2. Some dust on my iPad screen, had to blow away. Epsilon over 2. Then we get plus, and I have 1 over r squared, 1 minus 2 gm over r. And I will have L squared over 2, and then plus 1/2 dr d tau squared. Okay. And let me pretty much rewrite this as the following thing. I am going to call, well, the reason I'm going to rewrite this is because I'm looking at this here. And this looks like a kinetic term, right? Modulo the mass. So this is kinetic energy per unit mass, right? I have 1/2 v squared. Which means this must be my potential, my gravitational potential due to the Schwarzschild black hole, or the sun. Which means that 1/2 e squared is the total energy. Okay, so I'm going to call this my total energy, which the book uses some kind of cursive E for that, plus V of R plus KE, my kinetic energy. So that means that my potential, which is what we need to have, so we did all this work to isolate our gravitational potential, V of R. It's very cool. Okay, so my potential is going to have 1 minus 2 gm over r, which is just the Newtonian contribution for a massive particle, plus, and then let me go ahead and FOIL everything out. I'm going to have L squared over 2r squared, and then I'm going to have minus 2gm L squared over 2 r cubed. And let's go ahead and cancel out these 2's. This is very nice. Whoa, I didn't mean for that to happen. I don't know why it's doing that, but hey, okay. I give up. Auto shape detection. What's going on here? Well, if you look right here, this here is the Newtonian potential. This is the Newtonian potential if we added angular momentum to the system. So for an orbit, just using regular conservation of energy. Very cool. What do we have over here? And notice here we have 1 over r squared, or sorry, 1 over r for the Newtonian potential. That makes sense. Here we have 1 over r squared. That's a contributor for adding angular momentum. But here we have another Newtonian-like term, gm over r cubed, and that is the general relativistic correction. Okay, so this piece here is what you get from gr. Without this piece, so this last piece gives you everything, gives you all the, well, I already said correction pieces. So this last piece gives you the bending of light, the correct value for that. This gives you the correct orbits, and this gives you the correct perihelion precession of Mercury. It's all contained in this last piece. So if we did a purely classical mechanical analysis using Newton's law of gravity, we would end up getting this if we added angular momentum, we would never be able to get this piece unless we did this whole analysis from, keep in mind where we started with the Schwarzschild metric, right, which is a solution to the general relativistic field equation, Okay, we said we're using Gauss's law. We're staying away from the horizon. And then we took what we know from the geodesic equation, and we used the equivalence principle, which encompasses the geodesic equation, to finally work out our equation of motion here. Then we used the conserved quantities, Noether's theorem and Killing's Killing's equation, to identify what our conserved quantity is. Two of them, there's three, but the two here, they're important. And then we use those to rewrite our equation of motion, and in terms of an energy equation, total energy equals V plus T, kinetic energy, to extrapolate and get our Newtonian potential. Our Newtonian potential plus our general relativistic correction. Okay. Now I've actually went and plotted orbits for the for this equation here. I wonder if I can put that up here. So here are orbits, and on the left here you see I've plotted V of r epsilon equals 1, so we're massive. I set gm equal to 1, and then I gave it angular momentum values. I quantized them. So here's 0 angular momentum. You see, for 0 angular momentum, I just fall into the black hole. There's no stable points, mins or maximum. As we increase angular momentum, you see that I get a critical stable point, but I also get other stable points here where I can have orbits, and then there's a innermost stable orbit, or ISCO, which, if you remember, Sarah talked about that when she visited our class and talking about imaging of a black hole, what that image should look like. So here's the innermost stable orbit. Anything beyond that is actually going to spiral into the sun or the black hole. Okay, and now on the right here, you see I still have gm equals 1, but I set epsilon equal to 0. So these are light orbits. And so you see, as we increase the angular momentum, orbital angular momentum, we see that light even can have an innermost stable orbit, which is where the black hole shadow came from, that Sarah was talking to us about in class, and then other stable orbits for light. Okay, so we're gonna use this here now again in our next parts. This is always a good starting point to go find the potential for orbits, but what we're also going to do is use this now to analyze other solar system tests. So stay tuned.